All right, just a reminder to you all, you have a quiz on Friday which covers 10.4 and 10.5. The notification for that is up on eCampus as well. So always be alert of checking your eCampus because I always put the information up there ahead of time. All right, so this is just some reminders from what we learned about yesterday. There's really not much new material we're going to be addressing today. It's mostly going to be a review of yesterday and looking at some different types of graphs. You have to do your quiz. What do you have seventh period? Okay, so you can stay a little bit in if you need.
Yeah.
Okay.
Yeah, I was finishing the question. I don't remember the next class.
So did you want to do math? Is what you're saying?
Yeah, so I was curious about the lesson.
Sure. And then hand this other one to Gabby. All right. So first thing we're going to do is go ahead and graph this. So step one in graphing it is we're going to have to identify the points of discontinuity. Okay. So I'm going to rewrite this as y equals 4 over x minus 2 times x minus 2. And I'm able to do that because it's squared. Okay. So I'm just writing it out twice so that you have a better understanding of where each of those comes from. Okay. All right, so now that we've written it out twice, what we're gonna do, you guys need to move back to your assigned seats. Okay. We do not need extra distractions. I have people coming in late. I'm trying to teach this. We've already lost 10 minutes. We just do not need to be fooling around right now. All right. So anyways, as you can see, neither of these are going to get canceled out, correct? So because of that, what we're going to do is we're going to basically identify these as non-removable, okay? And they're non-removable because none of them are going to get canceled out, correct? So to find the point of discontinuity, we know x cannot be 2 because that would make it discontinuous, exactly. That means that these both would be considered vertical asymptotes, but what you're going to notice is these are identical. So we only have to list it out once. We have a vertical asymptote at 2 because they just would be the exact same thing. So they're just going to overlap each other. All right, so as for horizontal asymptote, is this bottom heavy, top heavy, or even or equal degree? Bottom heavy, which means we have a horizontal asymptote at y equals 0. Now to find the x-intercept, we're going to set our numerator equal to 0. So can that be solved? No, so we actually do not have an x-intercept. To find the y-intercept, you're going to take the entire equation and you're going to plug in 0 for x. Now it doesn't matter if you want to plug it into this one or the written out version, and they're the same thing. So you choose which one you feel better about plugging it into. So you're going to get 4 over 4, which is what? 1. So we're going to plug in, we plugged in a 0 and we got a 1. So we're going to start by graphing our vertical asymptote at 2. And then our horizontal asymptote at y equals 0. And then I'm going to plot my y-intercept, which is really the only point of information that I currently have. So we can do our domain now or later. Let's go ahead and do it at the end. So what we know is it's going to have this curvature on this side here. It's going to look something like this. But we don't know right now. We have no idea if it's going to reflect over to the other side, like reflect horizontally, or if it's going to reflect diagonally. So what we have to do is we have to do a test point. So what would be a good test point to test out? 4, that'll work. So we're going to take our equation and we're going to plug in 4 for x. So that's going to give us y equals 4 over 4, which is also 1. So we actually have a point at 4, 1. So this one's a little bit different. What you're going to notice is if you were to find more points, this one actually is reflected over what? Over the asymptote, exactly. Sorry, I meant to put a positive 2 there. So that's why the test point is so important. Does everybody see why we have to really test a point to see if it's going to be on the top or if it's going to be below? Yes.
Are we going to have to do the graphing on the test?
Yes, you will. But keep in mind, it's more of a sketch of the graph than it is accuracy. Yes.
If the x is equal to 2, how come it's not diagonal?
Diagonal?
Or like side
Horizontal? X equals numbers is always a vertical line. Y equals a number is always a horizontal line. Because this only takes on the x value of 2 at all times. Yeah, it's tricky because as I know x, you think. Yeah. All right, so from here, let's go ahead and identify our domain. X can be everything except for what value? 2. And y can be everything except for 0. And on the left and the right, where's the graph headed? Toward what? I didn't draw it too accurately. It's going downward a little bit toward the 0, the asymptote. All right, any questions about example 1? All right, perfect. So this one here, is it top heavy, bottom heavy? Bottom heavy, so it has the horizontal asymptote of y equals 0. Are any of these going to be removable? No. So we have a point of discontinuity at x cannot be -1 and x cannot be, you're right, +1 and -4. Sorry about that. Right after I said it, I was like, that's not right. Yes?
If you do remove them, does it have to go under the PLT?
Yep. But you would select removable instead of non-removable. Yeah, points of discontinuity, essentially, to make it more simplified, they're any point that's going to make the denominator 0. Okay, if that clears, it encompasses all types of things that will make the original denominator.
I have a question.
Yes.
So whenever it's bottom heavy, the horizontal asymptote equals 0?
Yes.
And if it's top, then the vertical equals 0?
No, if it's top, it just doesn't have a horizontal asymptote. The vertical is always based on the denominator and not have to do with the top heavy, bottom heavy thing.
Okay.
Yep. Yeah, it's tricky. I know there's a lot of different components to this. So we actually have 2 vertical asymptotes here. We have one at +1 and -4. And we don't have any holes, right? Because nothing got canceled. Exactly. To find the x-intercept, you're going to set the numerator equal to 0. Is that possible to solve? No. So there are no x-intercepts. For the y-intercept, you're going to take the entire equation and you're going to plug in 0 for x. Sorry, I'm like, there we go. So we got 5 over -4, which is -1.25. You see how I got it? Okay, perfect. All right, any questions about that? All right, so let's go ahead and graph this. So I'm going to start by graphing my 3 asymptotes. I have one at -1. Oh wait, it's at +1. I really want to put it at -1 today, huh? +1, and I have one at -4. And then I also have one at y equals 0. Yes?
Wait, so, I forget, why is it non-removable?
Nothing got canceled out. If nothing ever gets canceled out, it's not getting removed. Removable is only like if you had a factor on the top and bottom that canceled out.
Oh, okay.
Okay? All right. So from here, we're going to go ahead and plot the y-intercept at -1.25. Now what we're going to need to do is we're going to have to find some test points. So what we're going to do is let's plug in, if you were to plug in these values, I'll just tell you, if you plug in this, you're going to get a value about here and here. This is actually going to create this upside down U shape here. And this is one of the characteristics of these graphs. So what's different about this particular scenario that we haven't seen yet? We have, we have 2 vertical asymptotes, right? We haven't seen that yet in this class. When we have 2 vertical asymptotes, here's how it's going to look. You're going to have those 2 curved pieces, and then you're going to have one that's a U shape, because it's being broken an additional time, okay? So I'm telling you what it looks like, but of course, if you weren't sure, you could always plug in more points. And then we're going to have to test values on the left and the right in this one, because we don't know if it's going to be on the top or the bottom. So what's a good test point to try? 2. Let's try 2. So we plug in a 2. And we get 5 over 1, so 1 times 6, so 1 5/6, right about here. Something like that. So this one's going to have that curvature this way. And then, do we know where this side's going to go yet? No. So we have to test out a point. Which one do you want to try? All right, -6.
Where'd you get that point out of 5 over 6 on the top right?
I plugged in 2.
Yeah, but
She eyeballed it.
so okay, so never mind.
Oh, how did I know like about where to put it?
Yeah.
5/6 is like 0.8
Oh,
something.
So it's still under. Okay.
Yeah.
Eyeball.
Anytime your numerator is smaller than your denominator, you know it's going to be a decimal. So then we get 5 over -7 times -2. Yep, 5/14. So 5/14, if I find the decimal approximation for that, it's, 0.35. So 6 comma 0.35, like that. So it's going to look something like this. So we know that these graphs have these specific shapes, right, where they hug the asymptote. That's how we know what it looks like. But like I said, if you always want to get more points to be more confident about that, you can always plug more points in. Now the domain here is going to be a little bit tricky. There's not only one exclusion on X, there's how many? 2. It's going to be broken up into 3 pieces, though. So maybe that's what you guys were going for. So from -infinity to -4, that's this section of the graph right here. You see that? That's this. And then additionally, we pick back up and we go from -4 to 1. That would be this section of the graph right here. Okay. And then lastly, we pick back up and we go off to infinity, right? So it's going to be from 1 to +infinity. Now, as for the range could be anything except for what? 0. And lastly, on both ends, what's my graph approaching? 0, because it's getting flat. You see how it's getting flatter and flatter? All right. So for the homework,